All right, so we've been talking about continuity. You can think about that as drawing a graph without lifting up your pencil. Okay, nice, fluid, smooth graph. But we've been trying to shy away from looking at a picture, aka a graph, to determine if it's continuous or not. We've just been looking at equations to kind of help us determine, can we draw it without lifting up our pencil? So we're going to continue with some more examples today. Can you do me a favor and take a look at your homework, just for a second, on page 80 on the back? If you look at the directions at the top, the second sentence says, justify your responses analytically. That's kind of a big word. We're going to start seeing this word show up a little bit more often this year. Analytically just means by hand. So you're going to have to show some computation, okay, some work with that. So analytically means by hand, and we're going to do some more examples analytically today, okay, by hand. So if you want to make note of that, because there were some questions on Friday about that word, or at least from other classes. Okay? Can someone help me where we left off on Friday? Did we finish number 2 on page 77? We did? Completely? Okay. So we're just going to cover 2 more questions today. It's not going to take the whole class, which means you're going to have plenty of time to start this section's homework. Okay? Let's go ahead and take a look at number 3. We're going to analytically, okay, by hand, notice how we don't have a graph to help us out. We're going to try to determine if this graph or if this function for number 3 can be drawn without lifting up your pencil. Okay, is it continuous? Now we first have to determine, based on the way that piecewise equation looks, where are some special locations that might be a concern for us? Like where are some special points that we should really check to make sure if it's continuous or not? Do you guys think you can take a look at the way the equation is set up and determine where those special locations are? Yeah. Not necessarily where there's not a bar, okay? If there's not a bar, that means it's an open circle. We definitely got to check those, okay? But if there's a bar, we need to check it too. You're on the right track with that. Where are you looking for those bars, Maddie? Can you... The what? The inequalities, okay? So we're going to take a look at this section here. The bars are going to come into play in a second, okay? But based off of those domain sections, those inequalities, can you determine specific x values, specific locations that we need to check? Go ahead, Marie. 3 and 5. Okay, now why'd you pick those?
Because the piecewise functions end in circles.
Say it again.
The piecewise functions, like the qualifications, like end in circles.
Okay, they end and start there. So if you think about drawing a graph without lifting up your pencil, the first graph would be a line. We know we can draw that without lifting up our pencil. The second one is a U shape. We can draw that without lifting up our pencil. And the last one's a V shape. Okay, we can draw that without lifting up our pencil. The issue is where the line and the parabola meet up and where the parabola and the V shape meet up. Because at those beginning and ending spots, we want them to meet up, because if they're not, we're going to have that jump. Okay, they're going to be at 2 different heights. Okay, so notice how the first and second one begin and end at 3, whereas the second and third begin and end at 5. So those are special spots that we're going to have to check. All right, so we actually have to do 2 checks. We'll do one at a time. Okay. So how can we check continuity? What has to be happening graphically in order for us to be able to draw it without lifting up our pencil? Can you describe our definition of continuity? Yeah?
Continuity is when they meet the same place in a closed circle.
They meet at the same place at a closed circle. So we got to make sure there's a closed circle there. That's where Maddie's bars come into play. And then we also got to make sure the left and the right sides meet up. Okay? So let's first make sure there's a point, aka a closed circle. For this first one, we're just going to focus on the x value of 3, where the first one and second one equations begin and end. Okay? Is there a bar on either one of those equations for 3? The second equation, right? Okay? So what we're going to do is, we already know there's a closed circle, okay, because there's a bar, but let's go ahead and figure out the height of that closed circle, okay, the y value, where it's located. So we're going to take that x value of 3 and plug it into that second equation. Looks like we have 9 minus 6, which would be 3. Okay, so that's the height of our closed circle. So that's all well and good. Okay, that's part of what needs to happen to be continuous. You need a closed circle. But now we have to check the sides. Okay, do the two sides, the left and the right, meet up at that same point. So looking at your equations, the first equation shows up to the left of 3. So we'll say, as x approaches 3 from the left, we're going to check that first equation. If we plug in 3 to the first equation, we get 6 minus 3, which is 3. Okay, so it looks like the left-hand side is meeting up at that closed circle. That's good, because notice how they have the same heights. But now we have to check the right-hand side. That would be the second equation, shows up to the right of 3. And I think we already know this value, right? Because didn't we already plug in 3 into the second equation to find the point? Okay, so analytically, by hand, we're showing these computations. What are these numbers telling us about the graph at 3? Okay, this special x value of 3. Can we draw it without lifting up our pencil? Or do we have to lift up our pencil? What do you guys think? Yeah? We can draw it without lifting up our pencil. So we can say it's continuous at this specific location of 3 that we were checking. Okay, we're not sure about some other points, but at least at this one we know we can draw it without lifting up our pencil. Continuous at 3 because the left and right sides meet at a closed circle. We haven't lost it from last week, right? If we did, it's coming back. All right. We got another value to check, though, because we have another location where one equation ends and the other one begins. So we're going to go through the same analysis. This time we're just looking at the x value of 5. So is there a closed circle, aka a point at 5? Do we have a bar somewhere in the inequality section? Good, Marie? The last one, okay. So we know there's a closed circle. Let's figure out the height of it. Okay, the y value. We'll plug in 5. 5 minus 3, 2, plus 2, we got 4. Okay, so that's the height of our closed circle. Now let's check the sides. If we check the left side of 5, that would be our second equation. So let's plug in 5 there. We got 25 minus 10, so that would be 15. If we check the right-hand side of 5, that would be our last or third equation. We already did that before and we got 4. So what do you think? Continuous Discontinuous. If we have to lift up our pencil, can we classify what type we have? Yeah. How do you know? Yeah.
Because the two sides do not meet the same place, even though the one is in a closed circle.
There you go. All right, notice how the left-hand side has a height of 5, whereas the right-hand side has a height of 15. Okay, those are not meeting up at each other, so that's what's causing some type of jump. The closed circle is ending on the right-hand side, so if we think about it, the left-hand side has a height of 15 with an open circle, but the right-hand side has a height of 4 with a closed circle. It might be looking something like that. Okay, so height of 15, height of 4. Notice how that's causing a jump. So we'll say discontinuous, maybe even specifying jump in parentheses. Okay, we can classify the type at the x value of 5 because I think Marie said that the left and right side have different heights. Okay, they're not meeting up because the left and right sides do not meet. Can we see that fact based off the numbers? I know we don't have a picture, but can we analyze what the numbers are telling us? Make sense? Okay, so that one was a little bit more involved than the ones we did on Friday because we actually had 2 values to check. Sometimes you only have 1, but it's all based off of those domain sections, okay? Where does one graph end and the other one begin? We're going to step it up a little bit with this last one down here. Okay, for what values of A and B will the function below have a point discontinuity? Okay, that's the same thing as a hole. Sometimes I refer to it as a hole. What's our definition of a hole discontinuity? Or can you describe the way it looks? What do you think, Tori? Two sides come together at an open circle. Okay, so notice how the definition of a hole, the left and the right side have to meet, okay, so they have to have the same heights, but there is no closed circle or point at where they meet. Okay, so we want to try to figure out what's this A value and B value that would make this happen graphically. And we're specifically going to focus on -3 and 2 because notice how that's where the equations begin and end, based off of the piecewise function. Okay. Now, if you really take a close look at the domains, do you notice how there's not a single bar underneath one of those inequalities? So that's already signifying that we have an open circle somewhere, right? Because there's no bar, there's no closed circle. So the only thing we really have to check is that the left and the right side meet up. Because if there's no bar, we already know there's no open circle. So let's go ahead and check the x value of -3 first. We already know there's an open circle because there's no bar. But let's go ahead and check the sides. So as x approaches -3 from the left, that would be our first equation. If we plug in -3 into the first equation, -6 plus 3 would be -3. Let's go ahead and check the right side of -3. This is where it gets a little tricky because the right equation is ax plus 3b. Okay, we have a lot of variables going on there. But we're still going to treat it the same way. We're going to take this -3x value and plug it in for the x. We're still going to have an a and b, okay, but because that's what we're trying to figure out. But it's still going to act the same way. If we plug in -3 for x, we'll have a -3a plus 3b. Do you see that? Still works the same way. We plug it in for x. We just can't say it equals a number because we still have some variables. Okay. Now, in order for us to have a hole at this location, can we kind of combine these two results together somehow? If these two sides have to meet up, how can we show that idea mathematically? If they have to meet, if they have to be the same, yeah, we got to set them equal to each other. Okay, so we're going to eventually use that equation to help us figure out what is A and what is B. Okay, they told us we want to have a hole, so we need the sides to meet. We need them to be equal. We'll show that idea through an equation. Okay, let's do the same thing, and now we'll check the x value of 2. We already know there's a hole there, or an open circle rather, because there's no bar underneath an inequality. So let's go ahead and check the sides. As x approaches 2 from the left, that would be our middle equation. So if you plug in 2 for the x value, we'll have 2a plus 3b. And if we check 2 from the right, that'll be our last equation. So let's plug in 2 for all those x's, and we'll see what we get here. 2 squared is 4, half of 4 is 2, 2 plus 6 we have 8, minus 1 is 7. So in order for us to be guaranteed a whole discontinuity at this location of 2, the left and the right side have to be meeting up. Okay, they have to be equal. So it looks like we can write another equation to help us out here. Now let's not lose sight of our goal. Okay, it says for what values of a and b will the function have holes at -3 and 2. So we have this first equation that can help us with the -3 location. We have this second equation that can help us with the 2 location. How might you guys want to use those equations to help us figure out a and b? 2 equations, 2 variables. This is what's commonly referred to as a system of equations. Maybe you've heard that before? Yeah. We're going to combine them. Okay, now there's 2 methods that you might remember from Algebra 1 or Algebra 2 that you can use to help you solve a system. One of them is called substitution. I think that's the one we're more commonly familiar with. And the other one is elimination, where you kind of stack up the equations to cancel something out. Do we have a preference as which one we want to use? Do we want to see both of them? Do you want to do both? Just to see which one you guys are more familiar with or more comfortable with? Okay, so we'll do this twice. We'll try substitution and then elimination. Okay, so substitution, you have to pick either equation, it doesn't matter which one, and you have to choose a variable to get by itself, aka to solve for. It doesn't matter which one. So let's just first pick. Do we want to use the first equation or the second? Should it matter? Yeah.
It doesn't matter, but it'd be easier to use the first.
Why?
Because if you add over 3 and you divide by 3, it all equals 1, whereas you would have to do a fraction to
Okay, so if we can look into the future, if you were to think about solving the first equation for either A or B, you would eventually have to divide by a -3 or a +3, and if all of those coefficients are 3, dividing by 3 would just leave you with 1s, right? In the second one, you would eventually have to divide by either a 2 or a 3, but dividing 7 by 2 or 3 is going to leave you with a fraction. So it doesn't matter which equation, but there might be one that's more appropriate or strategic to pick. So looking into the future might not be a bad idea. So let's maybe work with the first equation. Which variable do you want to get by itself? A or B? It doesn't matter. Maybe one is more strategic than the other, but again, it doesn't matter. Yeah. Let's try A. Okay, so if we're going to get A by itself, We're going to have to subtract over the 3b. And then divide the negative 3. So now that we know what A is, okay, 1 plus B, what can we do with that 1 plus B value? This is where the name substitution comes in. Yeah.
Plug in for A in the second equation.
We're going to plug it in for A into the second equation, aka substitute it in. So if we do a little algebra, combining like terms, we can distribute. Looks like we'll have 5b, and if we subtract the 2 to the other side, that would leave us with 5. So our b value is 1. So we're halfway there. We figured out what b is. We also got to figure out a. Where do you want to go from there? Yeah.
Could we take substitute 1 into 1 equation for B?
Sure. Again, it doesn't matter which equation you pick. If you know the b value is 1, we can plug that in to help us figure out the a value. Doesn't matter. Maybe we'll use the second equation this time. If I plug in 1 in for b, we'll just be left with 3. So solving for a, looks like we get 2. All right, so in order for us to be able to draw this piecewise function without lifting up our pencil, okay, if you take a look at the very beginning equations, the a value must be 2, so this would have to be a 2x, and the b value has to be 1, which would make it a plus 3. If it's anything other than those values, you're going to have some type of discontinuity other than a hole, which would probably make it a jump. Okay, so it has to be that in order for you to have holes at those locations. Are we most familiar with the substitution method? I think that's what we normally use, maybe. Okay, let's try elimination. Is anyone really familiar with that or like that one? That's kind of my favorite depending on the mood. Yeah.
You try to make like one value be like positive and negative.
Right. We're going to make one value be positive and negative. We first, though, have to line up these two equations we have, kind of nice and organized. So if we were to write the first one just the way it is here, we're going to write the second equation underneath that, kind of like the old school way you guys add or subtract numbers, you know how you stack them on top of each other. Okay, we're going to stack these equations, but we're going to make sure the A's line up, the B's line up, and the number lines up. We don't have to do much rearranging in this case because they already line up the way they are, but you may have to move around some things to make them line up. Okay, so taking a look at this, we want to try to eliminate a variable, meaning get the numbers or the coefficients out front of either variable, again it doesn't matter which one, to be the same number but opposite. Okay, that way when you add them together they'll cancel each other out. Rebecca, do you see one that might be strategic for us to use already?
We could use 3, like you could just multiply the top equation by -1.
Okay, notice how the 3's in front of the b's already match. Okay, but we want one of them to be positive, one of them to be negative, that way they cancel. So in order to change a sign, you're going to have to multiply either equation, again it doesn't matter, by a negative. Rebecca specifically chose the first one. So if we multiply the first equation all the way through by a negative, that's going to switch all the signs. So we're now going to have a positive 3a, a negative 3b, and a positive 3. We're going to switch all those signs. So now if you were to add or combine the equations together, notice how we would have a 5a, because the 3 plus 2, The b's would now be eliminated. That's why it's called elimination, because -3, +3 is 0. It cancels out. And 3 and 7 together would give us 10. If we solved this new equation for a, dividing over the 5 would give us 2. And notice how that's the exact same value we got in the substitution method. So now that you know what a is, you can choose either equation, doesn't matter. Plug in 2 for a. Maybe we'll work with this one. If I plug in 2 for a, we'd have 4 plus 3b equals 7. Subtract the 4, divide the 3. You get the same b value. Those methods, we've seen them before, either one. Okay, so I don't really care which one you're more familiar with. I think most of us prefer substitution. Elimination, in my opinion, is a little bit easier as long as you can line them up and you can get the numbers to be the same. Notice how it was a little quicker, but it's just whatever your preference is. Okay, we hanging in there? All right, so that's the end of our section on continuity, okay, which means we're going to be ready for our partner quiz on Wednesday. All right. In the time we have left, I would like you to start your homework for this section, but after we take a homework quiz.